Okay, so in the greedy paradigm, now we are in the middle of spanning tree computation. So recall that spanning trees is just a graph, it is a subgraph of the given graph, which does not have cycle, and it connects all the vertices. So we already saw a fast algorithm. This is the greedy algorithm for MST by cut, the cut property. So cut is just a set of cross edges between A and A complement. Right. So what we do in this, the greedy choice is basically that whenever you have a cut situation, you should pick the min weight cross edges or cut edge, and that will be in the MST. So you introduce it and then you grow the set A. So that's the MST algorithm, greedy by cut. It runs in m log n, and it is also called Prim's algorithm. Any questions? So second property that we can use is cycle. So greedy by cycle. So here we will focus on I mean, just like here in this lemma 2, we showed that for any cut, min weight edge will be in every MST. Now we'll prove a theorem about a cycle. So what we want to show is the following lemma. So that we can call it lemma 3, I guess. So let C be a cycle in the given graph, and obviously it is a weighted undirected connected graph. Weight function is W. So let's also assume that integral weights, positive or negative. So we want to make a statement about the cycle's edges. So here you have to ask, can we claim that the min weight in a cycle will always be in an MST? Right, just like we proved in lemma 2 for a cut, can we say the same thing for a cycle? So that in general may not be true. So instead what we will prove is something about the max weight. So the max weight edge of C. What do you want to show about that? Right, so we'll prove a dual property here, and it will be true. So not about the min weight being there, but the max weight edge being absent. So the max weight edge of C is never in an MST. So we'll prove this opposite thing. So in other words, so this will give an algorithm, a greedy algorithm, because you can find a cycle, pick the max weight and delete it. Okay, and then proceed. So you can reduce the number of edges. So that will be the greedy algorithm, which is looking at properties of a cycle. So yeah, so for the proof of this, we need a diagram. So let's draw a spanning tree. Okay, so this is a spanning tree, and let us draw the cycle C here. So the cycle is, suppose this. Okay, so this cycle, let's put the weights. So this is weight 44, 13. In fact, this we can draw the blue edge. This is 80. This is 79. Okay, so this is the blue one is the cycle C, and so 80 and 79 are the same edge as the red ones, but they are included in the tree. Okay, so there is a spanning tree, and then within the spanning tree there is a cycle which is drawn in blue. So the three solid blue edges are not in the tree, and the dotted ones are in the tree. Okay, and these are the weights. So what is the max weight in this cycle? The 81, right? So suppose the spanning tree includes the max weight, which is the 80, the edge with weight 80. So let's call this E. And we can pick any other edge. It will have weight smaller than 80. So let's pick 44. Actually, I don't want to do that right now. Yeah, let's not do that. So the cycle is C. Its max weight edge is E, which is of weight 80. And there is a spanning tree which includes this edge E, and let us say this is a MST. Okay, that is the situation we want to contradict. So let T be an MST and E be the max weight edge of C. Okay, so this is the assumption we are making, that an MST contains this max weight edge of the cycle that is given. And now we want to get to a contradiction. Do you see how? So basically you have to change this tree T to some other tree T prime, which is even smaller weight. Right? So how do you do that? So basically one of the red edges you have to delete and add a blue edge. What is the choice? There is actually a unique choice in this example. So you want to delete that edge E, right? Because that is what the lemma statement says should not be there. So if you delete the edge E, what happens? Then the tree gets disconnected. So let's delete E. This MST gets disconnected into two. So if we cut the red tree by this black cut, so that red edge E is gone. So now you have these two red parts. Is there a blue edge? Is there an edge of the cycle which connects them? Since C was a cycle, so when you delete one edge of C, the cycle remains connected, right? So there is a unique edge which connects the two disconnected components of T, and it is of weight 44, right? So that edge 44 is what is important. This one. So when you disconnect the tree T by deleting E, there are these two black dots, and the edge between them is a cycle edge. That is still a bridge between them. So we should include this bridge. It's of weight smaller. 44 is less than 80. So that is the edge E0. There exists an edge E0 of the cycle that connects these two parts of T. Okay, so what we will do is swap E with E0. In the tree, getting another spanning tree T prime of weight strictly less than the weight of T. Is that clear? So if you delete E and you introduce E0, you add E0, then this tree T prime has weight reduced by the difference of E and E0, which is 80 minus 44. Right? So it's a MST. It's a spanning tree of smaller weight. So now this has become an MST, which is a contradiction. MST, if T was MST, then weight should not be reducible. Okay, so that's the contradiction stage. So this implies a contradiction. A contradiction to T, which implies that E can't be in T. Okay, that was the lemma. That in any cycle, so C was a general cycle that we had, arbitrary cycle we had picked, and E was its unique max weight edge. And suppose we had assumed that T is a tree which is MST, including this, then that gives you an E0 on the cycle with which you can swap it, exchange it, and that gives you a smaller MST. Okay, so that's the contradiction. Any question? So this is a major property of a cycle in a graph, which MST satisfies. Okay, so now we can give a completely different algorithm for MST using this idea, using this property. So find a cycle C in the given graph. This you can do by, how can you find a cycle in a given graph? Undirected connected graph, or any graph actually. How do you find a cycle? Yeah, so when you draw the BFS tree, BFS was the first algorithm you saw. So if once you do the BFS, you get a BFS tree, and if there is an extra edge, that gives you a cycle. So you will immediately get cycle in linear time, and then simply delete its max weight edge, because it is of no use in MST. Okay, so find a cycle and delete that edge, and then repeat. So when you repeat, then now you have like a graph with fewer edges. So every time you are reducing the edges, what is the halting condition of this algorithm? When there is no cycle, right? So when there is no cycle, then the algorithm halts, and at that point it's a tree. That's MST. So that's the simple, much simpler pseudocode than the previous one. So while E has cycle, you compute this edge in that cycle, delete it, and repeat. Okay, so the halting condition is that the graph has no cycle, so it's a tree, and just output that. So return E. Any questions? So this gives you the MST. Right? It's essentially a 2-line code to compute MST. So it's a very simple code, and again, it has this greedy property that it's not easy to come up with the greedy condition, and the proof is also non-trivial. So you have to come up with the right proof. What is the complexity of this algorithm? So how many edges are removed from the graph while iterations? Yeah, so the difference of m and n, m minus n, so m is always bigger, so around order m is the number of iterations, and in every iteration you have to find essentially a cycle which is BFS, and then max weight edge, which is overall, all that you can do in order n time. So how do you do BFS in order n? We said m plus n, right? How can you find the cycle using BFS in order n time? So it is the same BFS that you have seen before. It is just that you will not do it completely. So when your BFS works in a connected component. So after it has seen n minus 1 edges, if it sees one more edge, then you get a cycle already. Okay, so you don't do complete BFS, you do it only to find a cycle, and that can be done in order n. So you stop early. So every iteration is order n, and there are m iterations, so it's m times n. So while iterations are, they are actually exactly m minus n plus 1 many, because these edges one by one have to be removed to get to n minus 1 edges of a tree, spanning tree. And second property is that each iteration takes around n time. Okay, so which means that you have this result that MST cycle takes order mn time. Is that clear? Oh yeah, so right now we are not doing any such thing. This is just a simple implementation. Simple implementation is mn time. Yes, so what you are asking is the next question, can this be improved? Unsurprisingly, you want to use heap, and then this heap will not be min heap, but it will be max heap. So you have to say that you want to use max heap, because you always assume heap to be min heap. But here, since you want to extract the max, you need a max heap, and still I don't see immediately that you can do it. So that you have to think as an exercise. So can you do it or in fact, you know that MST you can do in m log n, we saw it last time, but can you implement this algorithm? In m log n time. Okay, so we are not doing it right now, but idea will be to be more careful with this. The while iterations seem to be m many, and each iteration takes n time, but somehow maybe you can do a cumulative analysis and get something better than mn. Let me leave that as a homework exercise, because I want to do the last problem in greedy paradigm, which is the mobile towers problem. So that would be our, I think, example 3. So here the problem is that this is also given in the assignment, in the practice assignment. So let's discuss that. So a mobile tower has a neighborhood which it covers. Covers the smartphone network basically within a distance. So mobile tower covers distance d. Let's say d kilometers. So if you put a mobile tower, then so within distance d, d kilometers, the circle is covered. So suppose you know the map of a town. So looking at the map, you want to cover all the houses, all the installations, using minimum number of tower locations. Right? That's the obvious problem. So what you are given is locations. So we'll simplify this. We'll not do this on a map. That will be the two-dimensional version. We'll only do the one-dimensional where you are given a road, and on the road you are given houses. Okay, so that's a simpler thing to start. So locations of n houses on a road. And in the output you want to place the minimum number of towers. So that each house is covered. So essentially you have this road, this is 0, and you have houses. And let's say so yeah, so I mean you have here just a 1D version of the problem, of the real problem. A road, and on this road axis you have these houses arbitrarily placed. You know their locations. So how will you place the first tower with the goal of achieving the optimum number of mobile towers such that every house is covered? Yeah, so the first tower, the question is, will you place on the first house or somewhere else? Yeah, so let us use the first suggestion, which is we place it on the house. Okay, so this is the first tower. So first tower covers the first house and houses up to distance d till this. And also it covers on the left, but there is no house there, so we don't have to draw anything. Then necessarily the second house, you have to put another tower because it's further away. And then maybe it covers both in one shot, right, and so on. So here we have placed 3 towers, each one at a house, right? And this is a greedy strategy because we are covering the first house and then we are deleting the houses which are covered, and then we are going to the next house and so on. Next house on the right, we keep moving. Do you think this will work? Why not? So that is idea 1. So place tower 1 at house 1. And remove the houses and then repeat. Yeah, so as some of you have guessed, this will not give you optimal in all the cases. There is no proof for it, and there is a counter example also. So that you can try. Okay, so you can find a counter example where this strategy will give you more than optimal number of towers. So what we want to do here is, what should you try next? Yes, so instead of putting the tower on the house, you should actually put it as far as possible. So where that D ends, you should put a tower there, with the hope that that further away tower will cover the first house and possibly also the second house. Right? That is a more clever strategy because it is using both the directions. Right now it seems that you are not using both the directions. You are only using that point where the house is. So that is an idea for which we will have a proof. In fact, this idea already tells you how to build a counter example. Because say this house which is just after the first D, right, that is getting missed. So you have to put two towers at each on one house. But if you put something in the middle, then it covers both, right? So that's already a counter example. So to cover that counter example, we use a better idea, which is place the first tower at distance D at D kilometers on the right. Of the first house. Now again remove the covered houses. And repeat. Okay, so this idea is you should actually put the tower here. So when you put it here, then it covers not only the first house but also the second house. So it covers everything up to this place. Right? And then what do? So now the first two houses are covered by a single tower, the green star. So you remove those houses, and then you have to repeat, which means you have to look at the third house and go further right and put a tower there. So put a tower here, which will again cleverly cover two houses. So for four houses, you only have to put two instead of three. Right? So that's a counter example as well as showing you the correct idea. Okay, so that is the pseudocode. So this will work. And what is the complexity of this algorithm? this is your first house. And so this is the t is your optimal that somebody has given. So let's make it prime, t prime. We want to convert it into this green one. The green one follows our idea too. So how do you convert t prime into t? Without changing the number of towers? Well, it is simple. You just say that I will exchange the orange one with the green one. So whatever t prime you are given, so there are many stars, suppose. One star here, then some orange star here, and then so on. And the green star placement is somewhere like something like this, so on. So what you have to do is you only exchange the first stars, respectively orange and green. Okay. You basically in t prime you remove the first one and put the green one there. Actually, I should not draw these ones. I'm only looking at the first one. So yeah, it will be, just write that. So define t to be t prime minus the first star with its first tower replaced by, let me label it correctly. So this is the T1. So just replace it by T1. Only the first one. Okay, so the first orange, we will delete it and we'll introduce T1 there. And then the remaining orange we will not touch. Okay, so the size of T prime and new placement, which is T, the sizes are equal. All you have to check is the validity. Does T cover all the houses? It does, right? Because whatever the first star was covering, orange star was covering, T1 covers that. And it's enough, right? Everything else we are not changing. So T prime, so the first, let's call that T prime 1. So whatever T prime 1 covered, is also covered by T1. So which means that T is also optimal. Okay, so that is the proof sketch, which you can build upon and complete the proof. Is this clear? Yes, so till now this has been the strategy in all our greedy algorithms, that you come up with a local decision strategy. So greedy idea common to all these problems that you have seen. So first is you make a local decision. And then second is, so once you know how to pick the first, then you have to come up with a process to reduce your instance and then repeat iteratively. Reduce the instance and repeat. And we have done only using iterations. We don't use recursion. Just a single call, so we just we can implement this iteratively. We don't make two recursive calls. Usually, if you do two recursive calls, then your time complexity will blow up. So you don't want to do that. Fastest is just this iterative for loop or while loop kind of implementation. So you make a local decision, reduce the instance, and then repeat iteratively. Right? This is the feature common to all these examples. And of course, for exam purposes, you need to give a proof. Right? So these three things are needed. You give the pseudocode written like that, and then you give a proof, or before that you give a proof why you are doing this. Why will it give the correct answer? Any questions? Okay, so since we have 5 minutes, so we can just mention one more problem, which is actually a harder problem, even to identify what decision to make. So this is the covering intervals problem. So here what you are given is a set of n intervals. On a line. Okay, so this is a 1D version. So you're given set of n intervals on the real line, or say on the, you have start and finish, similar to the job scheduling problem. So start and finish describes an interval, and you are given n such things. In the output, what you want is something different from job scheduling. What you want here is the minimum number of intervals which intersect with all these. So this is the set A of n intervals, and what you want to output is set B. So a cover B, which is a subset of A. That intersects with each interval in A. Okay, so this, so a subset of intervals which should be smallest. We also want to say that, and B is smallest. So smallest number of intervals which will intersect with all the intervals given. So basically, yeah, maybe let's just see the picture. So So your intervals A are, so 0 to 3, let me number them first. Okay, so the first interval is 0 to 3. Second is 2 to 5. Then 4 to 7. Then 6 to 11. 8 to 9, 10 to 13, and 12 to 14. Okay, so these are the intervals given to you. 7 intervals. That's the set A of intervals. What you want to output is the minimum number of intervals such that any interval you see in that picture intersects with something in B. Okay, so we call it a cover. It's an interval cover because one of the for any interval of A, one of the intervals in B overlaps. Okay, so in this picture it will be which one should be the first? 2 to, yeah, that's a good choice. 2 to 5 is good as first. After that, this long one, it seems to intersect with a lot of them. And the last, the third one is this last one, 12 to 14. Right, so the property of these three, so let's take B to be these three, 2 to 5, 6 to 11, and 12 to 14 is a cover, is min cover in fact. You can't do it in 2. Okay, so that of course you have to go home and check why you can't do in 2. So these three certainly work because you can see that any of the 7 intervals, so remaining 4 intervals you pick, they intersect with something which is in B. Okay, so it intersects for all intervals in A, there exists an interval J in B such that I and J intersect. That's the property. Okay, so B is covering, and also you cannot do below 3 intervals. Can't do it in 1 or 2 intervals. So this B is what you have to find by greedy approach. Okay, so that's your exercise. So find B by a greedy algo. Instead of 6, what did you say, 6 to 11? Yeah, if you take 8 to 9, sure, so you will take, you remove 6 to 11, so you take 8 to 9, and after that you will take, well, then you have to take Acha, okay, 12, 14, or you can also take 10 to 13. Yeah, that will also be another solution. But you can't do below 3. That's 3 is the minimum.